Hi, this is Alex from devstories.eu. PySpark Fundamentals, Episode 3 of 21. What if your code did not actually run when you typed it, but instead waited, analyzed your end goal, and mapped out the fastest possible route? You chain together filters, aggregations, and joins, yet your machine barely breaks a sweat. That is because it is doing nothing until you force its hand. This mechanism is called lazy evaluation, and it is the core engine behind PySpark DataFrames. A PySpark DataFrame is a distributed collection of data organized into named columns. If you are familiar with pandas, the concept feels identical. The difference is that a PySpark DataFrame splits its data across multiple compute nodes in a cluster. Historically, the foundational structure in Spark was the Resilient Distributed Dataset, commonly known as the RDD. The ecosystem has heavily shifted away from raw RDD manipulation. In fact, as of Spark version 4.0, direct RDD usage is no longer supported on Spark Connect. DataFrames are now the definitive standard, providing a strict API that allows Spark to automatically optimize your queries. That optimization relies entirely on lazy evaluation. Every operation you perform on a data frame falls into one of two strict categories, a transformation or an action. Transformations are commands that return a new data frame. Examples include selecting specific columns, filtering rows based on a condition, grouping records, or joining two separate tables. When you apply a transformation, PySpark does not execute the data processing. It simply records the operation. It updates an internal blueprint called the logical execution plan. You can write 50 consecutive transformations, and Spark will just quickly validate the syntax and update its graph. Here's the key insight. By delaying the actual execution, PySpark gives its underlying query engine, the Catalyst Optimizer, the complete picture of your data pipeline. The optimizer inspects your entire chain of transformations, rearranges them for maximum efficiency, and drops unnecessary steps entirely before a single byte of data is read from the disk. This blueprint remains completely dormant until you invoke an action. An action is a command that demands a concrete result. It either returns data to your driver program or writes data out to storage. Common actions include counting the total number of rows, collecting the data back into a local Python list, or commanding the system to display the top 20 records on your screen. The moment you trigger an action, the engine kicks into gear. It translates your optimized logical plan into a physical plan, distributes the tasks to the cluster workers, and runs the computation. Consider a standard data workflow. First, you create a data frame by pointing to a massive file. Then you join it with a separate table of user details. After the join, you filter the results to only include users from a specific city. Finally, you ask Spark to show the output. Because of lazy evaluation, Spark doesn't actually load the entire file, perform a massive distributed join, and then filter the results at the end. Instead, the optimizer looks at your final request, notices the filter, and pushes that filter operation up the chain long before the join happens. It selectively reads only the relevant records, drastically reducing memory usage and network traffic across the cluster. Your PySpark script is never a sequence of immediate commands. It is a set of instructions drafting an architectural blueprint, and the system only begins construction when you finally demand the end result. That's it for today. Thanks for listening. Go build something cool.